Welcome to a gas stoichiometry example session with Ms. Taylor. In this problem, we are looking for the volume or the number of liters of oxygen gas produced at STP from 1.25 kilograms of potassium chlorate. So let's organize the information we've been given. Okay, we have 1.25 kilograms of potassium chlorate. Now, first off, you should say, we don't ever use kilograms in these calculations for stoichiometry, so we need to change that to grams. Okay, and we are looking for liters of O2, and we were specifically said that conditions are at STP. Now, STP, you should remember, sorry about the dinging, for some reason the workspace is doing that. STP means 1 atmosphere and 273 Kelvin. So let's plan our attack for this problem. Now we are given grams, or well, we were given kilograms and we converted that to grams. So grams of potassium chlorate. Now remember, the only place we can go from grams is to moles. But once we have moles, we can go from moles of one substance to moles of another substance using mole ratio. But wait, not going to moles of KCl, we're going to moles of O2. And because we are at STP, now I'm going to write what we were using. Now again, because we are at STP, we can use a special relationship called molar volume to get liters of O2. And molar volume says that 1 mole at STP has a volume of 22.4 liters. Any gas, as long as it's at STP. So when we set this up, we're going to say 1,250 grams of potassium chloride. And we have to use molar mass. Now I already calculated the molar mass. It's 122.55. Sorry about that. Okay, and then our mole ratio from the balanced chemical equation, there are 2 moles of KClO3 to every 3 moles of O2. And again, because we are at STP, we can say that 1 mole of any gas, including our gas in question, has a volume of 22.4 liters. So when you plug that into your calculator, remember, multiply across the top, get an answer, multiply across the bottom, get an answer, top divided by bottom. Your final answer, rounding it to 3 sig figs, should be 343 liters of O2. And I'm running out of room on my screen there. Okay, I'm going to carry into a second problem using the same reaction. And I'm going to drop down here. Now we had 343 liters of O2 at STP. Now, it says, what volume of oxygen gas would be made from the same reaction if conditions were, 1.50 atm and 100 degrees Celsius? Okay, we want to think smarter, not harder. We have pressure, temperature, looking for volume. Okay, now don't we have pressure, temperature, and volume for initial conditions? We are going to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. So when you plug those in, 1 atmosphere times 343 liters divided by 273 Kelvin, because remember, temperature is always in Kelvin in these calculations. P2, looking for V2, divided by, and 100 degrees Celsius is 373 Kelvin. Okay, so algebraically, 1 times 343 divided by 273, multiply by 373, and then divide by 1.50, and your final answer should be 312 liters of O2. Now, what if you had not noticed that you could do that? How would you have solved the problem? Okay, alternately, you still could have used your first setup from part 1 and then converted grams to moles, and then mole ratio to get from moles one to moles of the other. I'm going to abbreviate a little bit here because I'm running out of space. But that would have gotten you 15.3 moles of O2. Then you could have used Pervnert, or the ideal gas equation, and plugged in 1.50 atmosphere, volume 15.3 moles, and because this is an atmosphere, we would need to use 0.0821 liter atmosphere per mole Kelvin, and then 373 Kelvin. Okay, notice all of your units cancel. The moles cancel, the kelvins cancel, and then when you divide by atmospheres, that will cancel too, and it will leave you again with the same answer, 312 liters of O2. So more than one way to solve gas stoichiometry problems. We want to think smarter, not harder.